Hi, my name is Jelilu Abdul, and I'm here with my colleague.
Hi, my name is Melissa Munoz.
Yeah, and our PI is Dr. Onajole. Today we're talking about design synthesis and antimycobacterial evaluation of some chemical derivatives bearing the imidazothiazole, imidazoxazole, and imidazopyrimidine scaffolds. Yeah, by way of outline, we'll be talking about a brief introduction about tuberculosis, and also we'll talk about the chemistry of the synthesis of the scaffolds of the derivatives of the compounds that we have. Yeah, and by way of introduction, tuberculosis is a contagious infection that mostly affects or attacks the lungs, but can also spread to some parts of the body like the brain and the spine. Most TB cases, as we all know, can be cured with antibiotics, but one has to be on the antibiotic for a long time, which is very frustrating to the patient. And also because of the certain strains that are produced by the causative agent, which is the Mycobacterium tuberculosis, these strains resist the antibiotics, which actually makes the antibiotics in combating the TB infections. TB infections can be categorized into two ways, which is latent and the active TB. Active TB is when someone is infected and because of weak immune system, the person can transfer or can affect other people. Whereas the latent TB, the immune system of the person is very strong, so it sort of stops the spread of the TB from one person to another, but the person still have the infection, which can potentially affect other people. But because of the strong immunity the person has, it stops it from spreading from one person to the other. So as a result of these strains, which makes antibiotic ineffective, scientists have to come up with new drugs that can fight these strains. Literature review has given us some information about some lead compounds such as imidazopyrimidine, imidazothiazole, imidazoxazole, and the likes, which proves to have some biological activity against TB infections. So it is based on this that we sought to produce some derivatives of these scaffolds, which we hope it will have some potency against TB infection.
Okay, so here we have the pathogenic strain that causes tuberculosis, Mycobacterial tuberculosis, and it's mainly an aerobic organism, but since within lung tissue, the populations of bacteria are inhomogeneous, there are both replicating and non-replicating strands available, and the formation of caseous granulomas within lung tissue create hypoxic conditions, which is what allows non-replicating strains to be available. And it is believed that these non-replicating strains are the causation of latent bacteria infection.
Yeah, there are, as I said, more literature on imidazothiazole, imidazopyrimidine, imidazopyrimidine, these scaffolds. Some literature has been found on them as to some compounds of these ones exhibit some potency against tuberculosis. These are some of them. The laminate, which is one of them, zolpidem and alpidem are all some derivatives of these scaffolds, and they are believed to have some potency against anti-tuberculosis, not only anti-tuberculosis, antiviral, antimicrobial, and anti-inflammatory diseases.
Okay, so here highlighted in blue, you can see the Imidazopyrimidine scaffold, and that is a component of each of these compounds on the slide. And these are just 3 of the more potent compounds that were in the published studies. So related studies for this class of compounds, all of these compounds exhibited a low minimum inhibitory concentration, and they all had the high selectivity of the QCRB target, and this is part of the cytochrome BD1 complex of the organism, and basically that just has to do with cellular respiration. In addition, exposed strains of MTB had an upregulation of the enzyme which codes for the enzyme which interferes with carbon flow, and this further suggested that the compounds inhibit energy production for the organism. In addition, all of the compounds showed a pattern in which hydrophilic substituents increased potency. So here you can see the Imidazothiazole scaffold, and these were basically intended to mimic the pyridine structure that you saw in the previous slides. So these compounds had the same QCRB subunit target. However, MTB strains that were cultured to be resistant to the inhibitor of QCRB, they were not resistant to the imidazole 2,1-B thiazoles in some cases, which may allude to the fact that they might interfere via a different mechanism. In addition, these compounds were not effective against non-replicating strands, and they all showed a pattern in which small polar substituents increased potency. Here we highlighted the Imidazoxazole scaffold, and there has been extensive medicinal research on these types of compounds due to their low toxicity, promising pharmacokinetic properties, and high biological activity. Derivatives usually have properties such as antimicrobial, anti-cancer, or anti-inflammatory. In terms of its relationship to MTB, it has been proven to be an inhibitor, and ring structures overall that have oxygen, like oxazoles or oxalines, are MTB inhibitors. Here we have a clinical trial candidate, which is a nitroimidazole oxazole, and this compound you see here on the slide affects both non-replicating and replicating strains of MTB. And it does so via 2 different mechanisms. So for non-replicating MTB, it releases nitric oxide via bioactivation, and that is toxic to the organism and it causes respiratory poisoning. In replicating strands, it interferes with mycolic acid synthesis of its cell wall.
Yeah, so in the synthetic route, the target molecules that will synthesize, which are the derivatives of the scaffolds, we will have to synthesize first the carboxylic acid of these scaffolds. Then we use the carboxylic acid as a starting material to synthesize our target molecules through multiple steps. So the first synthesis was that of the carboxylic acid derivatives, and it was done by reacting the chloroacetoacetate with either the thiazole or pyrimidine or oxazole, depending on which scaffold that you want to produce. So first have to get the chloroacetoacetate, react with it, then you get your ester, Now the ester was synthesized through the microwave-assisted reaction, where the thiazole or the pyrimidine or the oxazole reacted with the chloroacetoacetate in ethanol, in which the microwave was set up to 120 degrees Celsius at a pressure of 3 bar and a power of 80 watts for 2 hours. So after the reaction, then we have to use TLC. We use TLC to check whether the reactants have fully reacted to produce all the products, or whether you have a high yield of the product. Then the ester which was produced is now saponified. Saponification means reacting with a base, that is sodium hydroxide or either lithium hydroxide, then to get your acid. But you have to do a workup with HCl to remove any other base component that might be found in the system. So as I said, we use microwave synthesizer. So as you can see on the screen, on the left side is the microwave synthesizer. And as I said, the TLC plate, which indicated that almost all the thiazole or the pyrimidine, that is the reactant, has reacted. And the reaction, if you look at the reaction, which is indicated as R, you can see that we have a higher peak. At the top there is the product, and there's a faint peak in the middle indicating the reactant, the used up of the reactant in there. So this slide here also shows some of the instrumentations. On the left side is the Rotovap, and on the right side is the flash column chromatography. The Rotovap was used to concentrate our products so that we get rid of any solvent, ethanol, that is still inside our product. So after concentrating the product, then we use the solid one. We mix it with some silica to get the fractions, the flash column chromatography, which we use it to get the fractions of the various solutions that we have, and compare it with a TLC to make sure that we combine the right solution to get the component or the compound that we want to synthesize. So this slide here indicates the various fractions that we got from the flash chromatography and the TLC that go with the those solutions. So we compare the TLC and look at the various solutions and look at those that need to be combined to get the right products, and those that need to be discarded if they are unwanted products in the system.
So here we have a reaction under atmospheric conditions, and as you can see by the balloon on the top, it's filled with nitrogen gas. And then on the right, we have a reaction heating up to reflux with a condenser. So our project is still ongoing. We were in the lab up until the epidemic started and the school closed down.
Yeah, so as my colleague said, because of the pandemic that is going on, we couldn't finish the lab work, but we believe that we've done enough work, and we hope that after the pandemic, we will return back to the lab and continue the process and get our target molecules.
So we want to thank the Department of Biological, Physical, and Health Sciences and the McNair Scholar Program for their generous financial support of this project. Here are some of the references we use for the literature and the compounds
Yeah, if anyone is interested. Thank you very much for listening. We hope you enjoyed this presentation.